So since we have taken B is the matrix Bij, so Bij is I rth element of A and r jth element of A star, which is equal to j rth element of conjugate of A. So that is this. So we have written Bij is equal to summation Fkar, where Fk is Fi Fj bar. Now we know Fj bar is 1 upon Fj, so it will be Fi upon Fj. Now this Fk will be the principal character F1 if and only if Fi upon Fj is F1. Now since F1 is the identity element of the character group, so this thing is true only when Fi and Fj are same characters. So from the previous theorem, we have this result. Since Bij is sum of Fkar, which means sum of all the elements in kth row of the matrix A. So we know this sum is n when that k is equal to 1. That means for the first row the sum is n, and for all the other rows the sum is 0. That means whenever k is 1, this is n. And we know k is 1 if and only if Fi and Fj are same. That means I and j are same. So we can say Bij is n for I is equal to j and 0 for I not equal to j. So it means all the diagonal elements of the matrix B are n and all other elements are 0. So it can be written as n into identity matrix. So next theorem, we have next theorem which gives another orthogonality relation for characters, and this theorem says that summation Fr bar Ai Fr Aj, this is n for Ai is equal to Aj and 0 for Ai not equal to Aj. So from the previous theorem we have this result, A into A star is Ni, and we know the character group and the group G both are abelian groups, so this relation can be written as A star A is Ni. So A star A is Ni means this summation is n whenever Ai is equal to Aj and 0 whenever Ai not equal to Aj. Because Fr bar Ai, this is r ith element of A star, Fr Aj, this is r jth element of A. So Fr bar Ai, this is I rth element of, this is I rth element of A star and this is r jth element of A. So this summation is basically I jth element of the matrix A star A. And we know A star A is Ni, which means diagonal elements are n and others are 0. So this is I jth element of A star A. So I jth element will be n if I is equal to j and otherwise it is 0. So what this theorem basically says, now we know Fr bar at Ai, this is Fr Ai inverse. So this product becomes Fr Ai inverse Fr Aj. Now by the pointwise product of characters it will become not pointwise product, this is by multiplicative property of the character Fr Ai inverse Aj. So this summation becomes summation Fr Ai inverse Aj. This is n when Ai is equal to Aj and 0 when Ai is not equal to Aj. So this interprets that if Ai is equal to Aj, which means Ai inverse Aj, this is just identity element of the group G. So if this is identity element, then summation is n, and when these two are not equal, then this element is other than identity. So for the non-identity elements of the group G, this summation is 0. Which means if we take the images, if we take the image of identity element under all the characters F1, F2, Fn and take their sum, then it will be n, and the sum for any other element other than identity of the group G, that will be 0. So from this theorem we can also conclude this theorem. The sum of entries in the jth column of A. The sum of entries in the jth column of A is given by summation FRAG. Now jth column is corresponding to the element AJ. So R varying from 1 to n. This will be n if AJ is equal to identity element, and otherwise it is 0. The same thing which we have written here. For the identity element it is n, and for other element it is 0. So the next is Dirichlet characters. Up to this we have defined characters for an abelian group G. Now we define Dirichlet characters. Now in this section we have proved that for any finite group, finite abelian group of order n, there exist exactly n different characters. So in this section we will specify our group G to be the group of reduced residue classes modulo a fixed positive integer, let us say k. So here G will be a group of reduced residue classes modulo a fixed positive integer, let us say q. So we know for any integer k there are 5k different residue classes. So order of this group is 5k. And we know this is a abelian group. So there exist 5k different characters for this group. So let us say firstly we know that for this positive integer k, set of 5k integers a1 a2 up to a 5k set of 5k integers which are incongruent to each other modulo k, and each of which is relatively co-prime to k. And then for each integer a, the corresponding residue class is collection of all the integers x such that a is congruent to x mod k. And we have this group G. This is collection of all the residue classes a cap. And we define multiplication because this is a group, so this is group under some operation. So the operation here is multiplication, defined by product of residue classes is residue class of the product AB, product element AB. Now we know this group G, this is finite abelian group of order 5k, and here the identity element of this group G, that is residue class of 1 cap. This is identity element of group G. And inverse of A cap, this is another residue class B cap for which AB is congruent to 1 mod K. So now we define Dirichlet characters. What is Dirichlet character? Let G be this group of reduced residue classes mod K. Then corresponding to each character, because we know for a group for a finite abelian group, there exists exactly mm, equal to the number of elements in G, characters, distinct characters. So for each character f, we define arithmetical functions. Previously, the characters were complex valued functions defined on the group G. And now these Dirichlet characters, these are actually arithmetical functions which are defined on integers. So for each character f of this particular group G, we define an arithmetical function. Let us say chi, which is equal to chi f, because it is dependent on f, and we define it as follows. We define chi n to be f of n cap if n is co-prime to k, and otherwise it is 0. Now we know, being a character, this f is complex valued function defined on elements of G. That means defined on these residue classes, because the elements of G are here residue classes. We have to define arithmetical function. So we define chi at any integer n, at any positive integer n, as f of n cap, where n cap is residue class of n. If n is co-prime to k, then it is f of n cap, and if it is not co-prime to k, it is defined as 0. So this function chi is called a Dirichlet character modulo k. Chi is called a Dirichlet character modulo k. And the principal character here is obviously corresponding to the principal character f1. So we will denote the principal Dirichlet character by chi1, and chi1 will be given by f1. So f1 at any element is 1 always. So we can write chi1 is 1 if these are co-prime, and if these are not co-prime, then it is 0. So this will be called principal character. Principal Dirichlet character modulo k. So we have now a theorem which says there are phi k distinct Dirichlet characters mod k. Now because we define chi corresponding to f, so we know there are exactly phi k different characters for the group G. So there are phi k different Dirichlet characters for the Dirichlet characters modulo k. And we will prove in this theorem that each of these Dirichlet characters is completely multiplicative function, and it is periodic function whose period is k. And let's see what this theorem says. There are phi, this is theorem 6.15, you can read the statement from the book. There are phi k distinct Dirichlet characters modulo k, each of which is completely multiplicative and periodic with period k. That means chi of mn, this is chi m into chi n for all integers m and n. And secondly, chi of n plus k, this is chi n, because it is periodic for period k. This is true for all integers n. Now we have to prove conversely also. Conversely, if we have a function which is completely multiplicative and periodic with period k, and if that is 0 for all the integers n which are not co-prime to k, then chi is actually a Dirichlet character modulo k. So let us prove this. Firstly, we know there are exactly phi k distinct characters f for the group G. So there are obviously phi k different phi k characters chi f modulo k. Now this multiplicative property chi mn is equal to chi m chi n, this follows from the multiplicative property of the character f, because chi is defined in terms of f. Now if m and n both are relatively prime to k, say if let us say m and k is 1 and n and k both are relatively prime to k, then what is chi mn? If both are relatively prime to k, then mn is also relatively prime to k. So chi mn is, by definition, it is f of mn cap, and it is f of m cap into n cap, and by the multiplicative property of f, it will be f of m cap, f of n cap, and it will be just chi m into chi m. So this completely multiplicative property of chi follows. But if at least one of them is not relatively prime, so let us say mk is not relatively prime and nk, say if one of them, let us say m, which is not relatively prime to k, then mn cannot be relatively prime to k. So in that case chi mn, that is 0 by definition, and chi of m, that is also 0, because m is not relatively prime to k. So again both the sides are 0, so both the sides are same. So in both the cases chi mn is chi m into chi n. So we can say chi is completely multiplicative function. And secondly, periodicity. Now we know whenever A is congruent to B mod K, then GCD of A and K and GCD of B and K, they are same. And we know n plus K is congruent to n modulo K. So if n is co-prime to K, then n plus K is also co-prime to K. If n is not co-prime to K, then n plus K is not co-prime to K. So for both the conditions chi of n plus K, it is chi of n. So this is periodic function. Now converse. Conversely, if we have any function which is completely multiplicative and which is periodic, and third thing is this is 0 for all the integers n which are not relatively prime to k, then chi is actually a Dirichlet character. So we define f here on G, a complex valued function f on G by f of n cap, because the elements of G are now residue classes. So we define f at n cap. We define it by chi n if n and k are co-prime. Obviously, because n cap will belong to G if n and k are co-prime. So for the integers n which are co-prime to k, f of n cap is defined by chi n, and this chi n is given to be completely multiplicative function, therefore f is multiplicative. And secondly, this is periodic function, so this is non-vanishing function, so it will be a character. So this f is a character of the group G. Now if f is a character of group G, and we know chi n is f of n cap for n which are co-prime to k, and chi n is 0 for the integers n which are not co-prime to k, that means chi is a Dirichlet character. Chi is Dirichlet character modulo k. So now we find out Dirichlet characters, the values of Dirichlet characters for some integers k. Uh, Firstly, we will form tables. Firstly, for k is equal to 1. When k is equal to 1, we know for a group of reduced residue classes modulo k, that means for this group which contains 5k elements, there exist exactly 5k distinct Dirichlet characters. So for k is equal to 1, 5k is also 1. Similarly, for k is equal to 2, 5k is, for k is equal to 1 and 2, 5k is 1. So there is only one Dirichlet character mod k for these two values of k. That means there is only one Dirichlet character. There is only one Dirichlet character, namely the principal character chi1. So this is very easy. So there is only one Dirichlet character, namely the principal character. Chi1. Now for k is equal to 3. Now we know for k is equal to 3, 5k is equal to 2. So there are two distinct Dirichlet characters mod k. And we know this is periodic function and its period is k. That means it is periodic with period 3. So we will define it only for the consecutive 3 integers, and rest of the integers, the values at rest of all the integers are given by periodicity. So we make this table n 1 2 3, and we know for this k is equal to 3 there are two characters. First 5k is 2, so let us say the two characters are chi1 and chi2. Now chi1 is principal character. So principal character is always 1, as we have written that chi1 is 1 for n and k are co-prime, and 0 for n and k are non-co-prime. So now if n is 1, k is 3, they are co-prime, so this is 1. This is 2, this is 3, so again co-prime. 3 and 3 are not co-prime, so it is 0. And for the rest of the integers 4, 5, 6 and so on, we can calculate the value of chi1 by periodicity, because this is periodic function with period 3. So at integer 4 its value is equal to 1, at integer 5 its value is equal to the value at 2, similarly at 6 the value is equal to the value at 3, and so on. We can calculate it for all the positive integers. Now this chi2, how can we calculate this chi2? So we have two orthogonal relations. The first orthogonality relation says that for any character f, the sum of all the rows, sum of the first row which is corresponding to the principal character, that is n, and all other rows they are 0. Similarly columns, the sum of first column, that means the first column which is corresponding to the identity element of the group G, which I have written here. The summation FR AJ is n whenever AJ is identity element, and otherwise it is 0. So this means if we take the first element to be the, let us say a1 to be the identity element of the group G, that means the first column has some n and other columns has some 0. So we will apply all these results to find out the values for chi2. Now 1 here is identity element, because 1 cap, this is identity element of the group G. So chi2 at 1 cap, that is equal to f of 1. So f of 1, that is 1, because f at the identity element is 1. And again we know this 3 is not relatively prime to this, so at 3 it will be 0 always. But what is the value at 2? We know sum of this row should be n, where n is number of elements of the group. That means 5k. Sum of this should be 2. Sum of first column should be 2, and all other rows and columns should be 0. And that will be 0 only when this element is -1. So we will put -1. So we have to notice three things while making these tables, sum of first row should be 5k, sum of first column should be 5k for any k, and all other rows and all other columns should be 0, and all the entries here for all the integers which are not which are co-prime to k, because for the integers which are co-prime which are not co-prime to k, these entries are 0, but for the integers which are co-prime to k, these entries should be roots of unity, because for the integers which are co-prime to k, the value of chi at n cap is given by f at n. Sorry, value of chi n is given by the value f at n cap, and f is a character, and being a character, f of any element, that is just a root of unity. So all these quantities should be roots of unity. So let us take another example which will clarify. So let us take k is equal to 4, and then phi k again will be 2. So there are again two different characters. So let's make a table. We will now find the values for the integers 1, 2, 3, 4, because this is periodic function. So we can calculate all other. So again there are two characters, chi1 and chi2. Now 2 and 2, n is equal to 2 and k is equal to 4, these are not co-prime, so the entries at 2 are 0. Similarly 4 is not co-prime to 4, so these are also 0, and the rest of the values should be first row sum should be 2, so it is 1 1. First column sum should be 2, so it is 1 1, and other rows and other columns should be 0, and this entry should be a root of unity, so it is only -1. So let's take another one more example. K is equal to 5, phi k is equal to 4. When k is equal to 5, the phi k is 4. So let us make this table. Now n is 1, 2, 3, 4, 5. Now phi k is 4, so there are 4 distinct Dirichlet characters. Let us say chi1, chi2, chi3, chi4. This is principal character, and 1, 2, 3, 4, all the integers are co-prime to k, so all these entries are 1, 1, and 5 is not co-prime to k, so it is 0. Similarly 1 is identity element, so all these are 1 at 1. 5 is not co-prime to k, so all these are 0 at 5. Now we have to put all these values such that columns and rows should be 0, and all these numbers, they should be roots of unity. So to fill this table, one more thing we have to take care, and that is we have this result. If a raised to, let us say, r is e, which means if order of a is r, then we know f of a raised to r is 1. We have proved this result. If a is element of the group G and order of a is r, then fa is actually rth root of unity. So here, firstly, we find out the order of 2. So 2 into 2, that is 4, and this is not congruent to 1 modulo 5, because here k is 5, so we have to take modulo 5. Then that means 2 square is not equal to 1 in modulo 5, so order of 2 is not 2. Then what about 2 cube? 2 cube is 8, and 8 is also not congruent to 1. 2 raised to 4, 16. 16 is congruent to 1 modulo 5, which means order of 2 is 4. Order of the residue class of 2 is 4. That means for this element 2, all these entries are fourth root of unity. So if these are fourth root of unity, then they should be 1 minus 1 iota minus iota. So let us take 1 is written already here. So let us take this is minus 1, this is iota, this is minus iota. Now similarly we calculate order of 3 and 4. Now 3 square is 9, and this is not congruent to 1 in modulo 5. Then 3 cube, this is 27, again not congruent to 1. 3 raised to 4, 81, again it is congruent to 1 modulo 5. So order of 3 is also 4. So entries should be 1 minus 1 iota minus iota here also. Then what is order of 4? So 4 square is 16 and that is congruent to 1 modulo 5. So order of 4 is 2. So the entries under 4, they should be only 1 and minus 1 because they are square roots of unity. So we have to put all these entries in such a way that all the columns here and all the rows here, they should be, sum should be 0. So if we put, now we know 4 square is 1. That means entries in this row, they can be only 1 and minus 1. And we know this column, sum of this column should be 0. So we will have to write 1 twice and minus 1 twice. And now sum of this row should be 0. So 1, 1, minus 1. So this entry will be obviously minus 1. Similarly 1 minus 1 iota. So it should be minus 1. 1 minus 1 minus iota. It should be iota. And of course these entries should be 1 minus 1 iota minus iota. So this is how we can complete these tables. So let us take one more example. Let us take k is equal to 6, and for k is equal to 6, phi k is 2. And this is easy to make this table because phi k is 2, so there are only two characters, chi 1 and chi 2. At 1, these are 1. Now 2, 3, 4 and 6. These are not co-prime to 6, so all the entries here are 0. Now 5 is co-prime to 6 and this row should be, sum of this row should be 2, so this entry should be 1, and this column, sorry, this row should be 0, so this entry is automatically minus 1. So this is easy. Now let us take k is equal to 7. For k is equal to 7, phi k is 6. So let us make this table. We will understand from this example more clearly. So there are 6 characters. Of course, we have to define these characters in such a way that all should be distinct characters. So the very first row is 1 because of this is identity element. 2, 3, 4, 5, 6, all these are co-prime to 7. So these are 1. And the last row 7 is not co-prime to 7. So all the entries in the last column, they are 0. Now what about the rest of the entries? Now here, firstly we find the orders of all the elements. So for element 2, 2 square, 4, which is not congruent to 1 mod 7. 2 cube, 8. So 2 cube is 1 modulo 7. So order of 2 is 3. That means the entries in this column, they are cube roots of unity. And they should be 1, omega and omega square for the element 2. Then we will find the order 3. We will find the order of the element 3. So 3 square is not congruent to 1. 3 cube, which is 27, again it is not congruent to 1. 3 raised to 4, not congruent to 1. 3 raised to 5, 3 raised to 6 is congruent to 1. So here the entries should be 6 roots of unity. So it should be 1 minus 1 omega minus omega omega square minus omega square. Similarly, for the element 4, 4 square, 4 cube, 4 cube is congruent to 1 modulo 7. So these are also cube roots of unity, 1 omega omega square. Then for 5 order of 5 is 1 when you calculate this. So the entries should be 1 minus 1 omega minus omega omega square minus omega square, and 6 has order 2. So the entries should be only 1 and minus 1 because they are square roots of unity. So let us put the entries. Firstly, we start from 6. 6 is a square root of unity, 1 and minus 1, and the column should be 0. So we will write 3 times 1 and 3 times minus 1. So let us write here minus 1, 1, minus 1, 1, minus 1. Now this row should be 0. So firstly, 2 cube is 1. So for this column, we have to enter the values 1 omega omega square. So let us put the values 1 omega 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 square omega square, because we know 1 plus omega square is 0. So if we write twice 1 twice omega twice and omega square twice, the sum will be 0 in this column. And other entries, we have to take care that all the columns and all the rows should be 0. So here again for 4 we have to put this 1 omega omega square, and for 3 and 5 we have to put 1 minus omega, and so on, these values. So in this column now 1 occurs twice, minus 1 occurs only once. So we have to put the values such that the sum of the rows should be 0. So it will be like this: minus 1 minus 1 1. Now we know entries for the element 4, they should be 1 omega omega square, but the characters should be different. So if this takes values omega at these 2 points and omega square at the 2 points, so we have to differentiate. For the differentiation, we take omega and omega here, and here it is omega square. Otherwise the two will be same. So omega omega square, similarly here omega omega square. So what we have to put in other 2 columns such that sum of rows and sum of columns should be 0, and all the entries these can be used. So here 1 omega omega 1. So both the entries should be omega square, so that this column will be 0. Similarly here 1 minus 1 omega omega square. So we can put the value minus omega and minus omega square here. So let us write here minus omega and minus omega square. Then for 5, chi 5, we have to take care of this also: 1 minus 1 omega square minus omega. So we can use only omega and minus omega square here. So let us use 1 omega omega square, 1 omega and omega square. Omega minus omega square, it should be Let us say this is omega, then this should be sorry, I have to calculate it. So let us make it again.